Welcome to next lecture. In the previous lecture, we discussed single phase semi-converter with the three configurations, and we discussed about all waveforms for the three configurations. Okay, the topic was not completed. Now, in this lecture, let us start with the equations, basic equations. Of course, this is a continuation for the previous lecture. And if you see here, output voltage, output current and source current, these three waveforms are same for the three configurations. Therefore, the calculations based on these three waveforms, V0, I0 and IS waveforms, are same for the three configurations. So what I can do here, for three configurations, what all the equations we are going to derive now, these are applicable for the three circuits. Okay. Now, first let us look into average output voltage. If you see the waveforms, you can notice that the periodicity of V0 waveform is pi. Therefore, 1 by pi integration from alpha to pi Vm sin omega t, integration is with respect to x-axis d omega t. Therefore, Vm by pi integration for sin omega t is minus cos omega t, and the limits are from alpha to pi. Okay. Therefore, we will get V0 is equal to Vm by pi multiplied with 1 plus cos alpha. Okay. Now, either from the equation or from waveform, we can get one important conclusion. Observe carefully here. In the single phase full converter circuit, what was the observation? When alpha was increased beyond pi by 2, then majority of V0 waveform was entered in the negative side. Hence, we concluded that average output voltage was negative when alpha greater than pi by 2 in previous circuit. That was single phase full converter. But now, you just imagine if I increase alpha beyond 90 degree, due to this freewheeling action, this output voltage waveform will never enter in the negative side. So what I can say here, for any alpha, average output voltage is positive because of the freewheeling action. Even if you increase alpha beyond pi by 2, average output voltage is still positive only. Due to unidirectional property of the devices, average output current is also positive. Okay. So, by using these two conclusions, we can say the product V0 into I0 product is positive. What do you mean by that? When the power delivered to the load is positive means the direction of the power flow is from AC to DC always. Therefore, this conclusion we can put it in quadrants, something like this. So whatever the firing angle is, this particular semi-converter circuit will give you first quadrant operation only. Okay. So for any alpha, V0 is positive, I0 is also positive. Hence, we will get the power flow direction is always from AC source to DC load. Therefore, what we can conclude here, semi-converter circuit will always give rectifier operation only. Semi-converter circuit will always give rectifier operation only. In other words, from the drive's perspective, semi-converter circuit is preferable for forward motoring operation only. Okay. Whereas in single phase full converter, we got forward motoring as well as reverse regenerative braking. But now half controlled rectifiers, that is the reason half controlled rectifiers, why it is called half controlled, because average output voltage can be controlled from 0 to positive magnitude only. So this particular circuit is preferable only for forward motoring operation. Whereas in full converter circuit, single phase full converter circuit, it was 0 to positive value, negative value also, and hence it was named as a fully controlled rectifier. Okay. Now observe carefully, this is half controlled rectifier, but it is full wave rectifier. Okay. It is a bridge rectifier, it means full wave rectifier. Half control and half wave both are different, right? So this is about output voltage equation conclusions. Next, let us look into conclusions based on source current waveform. So what is the first calculation I want? RMS value for this source current waveform. This is a quasi square waveform. In fact, we discussed RMS value for the same waveform in our basics class. Okay. So if you recollect from that, I can write RMS value of source current. First let me write down IS square is equal to I0 square multiplied with function duration, that is pi minus alpha. Because of the symmetric nature, you have to write down for half cycle only. Therefore, we will get RMS value of source current is equal to I0 multiplied with square root of pi minus alpha divided by pi. IS is equal to I0 multiplied with square root of pi minus alpha divided by pi. Okay. Next. Now let us look into power factor definition. How to find out that? Input power factor can be defined as power delivered to the load divided by source volt ampere. As we assume that load is a current stiff load, you can say V0 multiplied with I0 divided by Vs into Is. Now what is V0? Vm by pi multiplied with 1 plus cos alpha multiplied with I0 here. Okay, multiplied with I0. Denominator Vs can be written as Vm divided by root 2. Is just now we derived I0 into root of pi minus alpha divided by pi. So here I0 and I0 can be cancelled, Vm and Vm can be cancelled. Therefore, from this input power factor can be expressed as root of, now calculate carefully here, root of, see this is it will be pi, so here root pi, therefore what we can have, root of 2 by, let me write here, root of 2 by pi into pi minus alpha multiplied with 1 plus cos alpha. Okay, this is the expression for input power factor, right? This is the expression for input power factor. We can also write down this expression as 2 root 2 by root of pi into pi minus alpha multiplied with cos alpha by 2 into 1 more cos alpha by 2. What is the reason for this? I just wrote 1 plus cos alpha as 2 multiplied with cos square alpha by 2. Okay. Now here this cos alpha by 2, in the earlier waveforms explanation we told that it is a DPF. But in our previous lecture we already studied that input power factor means distortion factor multiplied with displacement power factor. As this term is already DPF, you can say that this particular term is DF, that is distortion factor. But what is distortion factor where DF is equal to IS1 divided by IS. Therefore, from this IS1 can be expressed as distortion factor multiplied with IS. So, by substituting distortion factor, now let us see what we will get expression for IS1. IS1 is equal to distortion factor multiplied with RMS value of source current. What was the expression for distortion factor? 2 root 2 divided by under root pi into pi minus alpha multiplied with cos alpha by 2 into IS is equal to I naught into root of pi minus alpha divided by pi. Therefore, RMS value of fundamental source current is equal to 2 root 2 by pi. This pi minus alpha will get cancelled out into I naught into cos alpha by 2. This is the expression for fundamental RMS value of source current. Next, we already discussed the distortion factor and input power factor also we defined. Now, what is required for us? THD in source current. THD in source current. Now, as we discussed in detail in the previous lecture, let me write down the formula directly. Under root 1 by df whole square minus 1. Therefore, THD in source current is equal to square root of 1 by df whole square. Now, I have df here. Therefore, we will get pi into pi minus alpha divided by, so I just squared it, okay. So divided by 8 into cos square alpha by 2 minus 1. This is the expression for total harmonic distortion in source current. Now observe carefully here. In case of single phase full converter, THD in source current was simply 48.43%, irrespective of firing angle. Now, in case of single phase semi converter, it is expressed as function of alpha. Okay. So, what do you mean by that? By selecting suitable firing angle in single phase semi converter, it is possible to control THD. In single phase full converter, we got THD was 48%. But as per IEEE standards, that THD should be less than 5%. So in order to reduce that number below a satisfied value as per IEEE standards, there is a need of source filter at input side. Now that filter design is simple in case of single phase semi converter because there is one more freedom of choice, that is firing angle also. Of course, completely less than 5% is very difficult to obtain with the firing angle control, but it can be controlled to some extent. But what is the limitation of single phase semi converter? This particular circuit is suitable only for motoring application, but not for braking application. Okay, that is what the limitation here. Now, in comparing with the power factor, single phase semi converter has better power factor in comparing with the single phase full converter. Okay, so if you conclude high level, full converter single phase, semi converter single phase, power factor wise semi converter is better performance because of the freewheeling action. Motoring and braking wise full converter has better performance, so you can select depending on the application. Okay, so this is about conclusions on source current. Now let us look into configuration wise calculations. Till now we discussed common calculations for the three configurations. Now let us go with the configuration wise. So if you look into these two waveforms, I can understand that conduction angles are varies from interval to interval. Okay, now what I will do, by using these two waveforms, I would like to calculate average and RMS values for thyristor current and diode current. Follow carefully. For configuration 1, for configuration 1, so what I would like to find here, average value of thyristor current, area under the waveform, that is I0 multiplied with pi, periodicity is 2 pi, therefore IT average we will get I0 by 2, right? Next, average value of diode current, this is also area I0 into pi divided by 2 pi, that will give you I0 by 2. Okay, that will give you I0 by 2. Next, I would like to find RMS value for thyristor current. That means rectangular function magnitude square into function duration pi, denominator 1 cycle time, that is 2 pi. Therefore, we will get I0 divided by root 2. Next, RMS value for diode current, magnitude square into pi divided by 2 pi under root. This will give you I0 by root 2. So these are average and RMS values for thyristor current for configuration 1. Next, let us look into configuration 2, SCR and diode current waveforms. Now I can identify here SCR is conducting for an interval of pi minus alpha. Therefore, pulse duration is pi minus alpha. Whereas diode is conducting for an interval of pi plus alpha. Okay, so let us use these conclusions in order to find average and RMS values for thyristor and diode currents. IT average, area under the waveform, that is I0 multiplied with pi minus alpha, that is area, divided by cycle time 2 pi. So it will give you I0 multiplied with pi minus alpha divided by 2 pi. No further simplification, you can just leave it like that. In fact, both steps are same. Average value of diode current, area under the waveform, that is I naught multiplied with pi plus alpha, divided by periodicity, that is 2 pi. Next, RMS value of diode current, magnitude square multiplied with pi minus alpha, pulse duration, over a cycle time of 2 pi under root, then it will give you I naught multiplied with pi minus alpha divided by 2 pi. Next, RMS value of diode current, I naught square multiplied with pi minus alpha divided by 2 pi. I am sorry, here it is a pi plus alpha. Diode conduction interval is for pi plus alpha. Therefore, it will give you I naught multiplied with pi plus alpha divided by 2 pi. These are average and RMS value calculations of thyristor and diode for configuration 2. In the similar way, let us look into for configuration 3 the waveforms. SCR is conducting for a period of pi minus alpha, where diode is conducting for a period of, diode in the sense freewheeling diode, is conducting for a period of 2 alpha in one cycle. Therefore, how to write average and RMS values, let us see. Now here, average value of SCR current, area under the waveform, I naught multiplied with pi minus alpha divided by 2 pi. We can just leave it like that. Next, average value of freewheeling diode current, I naught multiplied with 2 alpha divided by 2 pi in one cycle. Okay. Therefore, it will give you I naught multiplied with alpha by pi. I naught multiplied with alpha by pi. Next, RMS value of SCR current, magnitude square multiplied with pi minus alpha divided by 2 pi under root. This is equal to I naught into root of pi minus alpha divided by 2 pi. Next, RMS value of freewheeling diode current, I naught square into function duration is 2 alpha over a cycle time of 2 pi. Hence, this is equal to I naught multiplied with alpha by pi. Now, let us discuss one special case particular to this configuration 1. Okay, just recollect from your previous lecture. Configuration 1 is named as a symmetric configuration, where upper half devices are thyristors, lower half devices are diodes. So, a previous waveform I just quickly had drawn here just for reference. What are the conducting devices alpha to pi? Okay, T1, D2 devices were in conduction. Listen carefully, one special case, it looks interesting also. Pi to pi plus alpha, the devices are T3 and D2, and T3 and D2 provided freewheeling action. Next, pi plus alpha to 2 pi, T3 and D4 devices, right? T3 and D4. Let us look into one special case, especially for symmetric configuration. What is a symmetric configuration? Upper half devices are thyristors, lower half devices are diodes. Okay. Now, for this particular circuit from the previous lecture, you can just quickly draw the output voltage waveform. Okay, this is from our previous lecture V0 waveform. just recollect what are the conducting devices from alpha to pi. Those are T1 and D2. Okay, T1 and D2. Now at pi plus alpha, T3 will start conduction. Up to that, upper half T1 will continue the conduction. Lower half D4 will start. Okay, lower half D4 will start. Next, pi plus alpha to 2 pi, T3 and D2, T3 and D4 are in conduction. Therefore, output voltage will be followed by VBA, third and fourth position devices. 2 pi to 2 pi plus alpha, what are the devices in conduction? T3 and D2, and they are provided freewheeling action. Now again T1, D2 will be repeated. Now important point here is 2 pi to 2 pi plus alpha is same as from 0 to alpha also. Okay. Now what is the special case in this particular circuit? For example, if we give alpha closer to pi, this is what a special case. When you supply firing angle very close to pi, then what will happen? Follow carefully. Suppose if alpha is given nearer to pi, what do you mean by that? T1 will be triggered nearer to pi, isn't it? T1 will be triggered nearer to pi. So until this instant, T3, D2 anyhow it is already conducting, because D2 conduction is independent of firing angle, isn't it? So D2 started when VBA is a negative. So D2 will readily start from 0. Similarly, D4 will start from pi itself, because diode's conduction is not depending on firing angle. Only here adjustment is upper half devices. If T1 is triggered very close to pi, what is the concept? Due to heavy inductive property of the load, T3 will conduct up to T1 is triggered. That is what our basic idea. But observe carefully, if alpha is given very close to pi, T1 is, see here T1 is going to be reverse biased immediately after pi. What do you mean by that? When T1 is going to be reverse biased, at that instant we are giving a firing angle to T1. Suppose if T1 is very close to pi, okay, so T3 will get reverse bias only from this instant to pi, very short period of time. We studied in our thyristor characteristics, for SCR to complete its turn off process, we should give sufficient time for SCR to be safely turn off. Okay, because SCR is a minority carrier device, whatever stored carriers, it has to be removed. For that, there should be sufficient time. Now, if T1 is given at alpha, T3 will be reverse biased for a period of pi minus alpha. So T3 will get sufficient time, there is no problem. But when the problem will come into picture, if T1 is triggered very close to pi, then pi minus alpha duration will be very small. In that period, T3 may not complete the recovery process. Then what will happen? T3 device fails to turn off. Okay, the line commutation of T3 device will fail. Then if line commutation of T3 fails, what happens here? T3 will continue to conduction. T3 will continue to conduction. If line commutation of SCR fails, what happens? Whenever it is forward biased, without giving gate current itself, device will start conduction. Therefore, T3 will continue to in the conduction. So what happens here? T1, even though it is fired or triggered at angle which is very close to pi, T1 will not start conduction because T3 is continue to conduction. If T3 and D4 are continue to be in the conduction, what is the scenario? Okay, output voltage is going to be appeared like this, right? Output voltage is going to appear in this way. So observe carefully, this circuit is a full wave rectifier, but output voltage is appeared as a half wave rectifier circuit. This concept is called half waving effect. Half waving effect. Therefore, in this bridge circuit, thyristors and diodes are designed by calculating full wave calculations, but this particular device is going to carry it for half cycle completely. Therefore, half waving effect will give undesirable effects, right? So this concept is called half waving effect, but this concept will not appear in asymmetric configuration. Okay, I want you to analyze that. In this particular case, asymmetric configuration, half waving effect will not appear. Therefore, one of the basic problem in case of symmetric configuration is a half waving effect when alpha is more nearer to pi. In order to overcome this problem, one of the common practice is a freewheeling diode will be placed across this particular load. Okay, in order to avoid this freewheeling diode, what is the basic requirement? You should operate this semi-converter circuit not nearer to alpha, very close to pi. Okay, if you give sufficient time for devices to turn off, then there is no need of this extra freewheeling diode. That is one aspect. Now, another aspect, another comparison of these two configurations, is, now observe carefully. For example, I have a thyristor. Okay, I have a thyristor. There are, see, observe carefully here, just for explanation I just elaborated these terminals. This is the gate terminal, this is cathode terminal, right? Gate drive circuit can be connected in between these two, terminals. Gate drive circuit, this is a drive circuit. Okay, gate drive circuit is connected between gate and cathode by using some isolation. So whatever we discussed in the thyristor characteristics, that will be placed over here. Now observe carefully, in these two circuits, just now we completed analysis of these two circuits. These two circuits resulted into same value of average output voltage, same value of source current RMS values. What do you mean by that? Same output voltage and same harmonic content in the source current. That means both the circuits have exactly giving same performance in the output as well as source side measures, right? But there is one small observation if you do very carefully here. For these two thyristors, T1 and T3 devices, cathode is common. One very important point, cathode is common here, right? Therefore, for these two thyristors, cathode is common. Therefore, one particular gate drive circuit, okay, this is a gate drive circuit, is connected between cathode here. That means this gate drive circuit is connected cathode of the two devices, because cathodes of the two devices are at the same point only. One more point, T1 and T3, both the devices are conducting in different intervals, isn't it? First half cycle one thyristor, second half cycle another thyristor. Therefore, one gate drive circuit is sufficient. It can supply gate current for one particular device in the positive half cycle, another device in the second half cycle. Therefore, in the symmetric configuration, single gate drive circuit is sufficient. Single gate drive circuit is sufficient. Whereas in this circuit, you have to use two gate drive circuits. Okay, You have to use two gate drive circuits. What is the reason for that? Because cathodes of the two devices are different. Okay, therefore the point is symmetric and asymmetric configurations, even though both the circuits are having same performance measures, hardware requirement or control is somewhat complicated in the sense hardware requirement is high. Okay, so this circuit will be more costly. However, both the circuits requires two thyristors, two diodes, but the way you are connecting demands more hardware in case of second configuration. But in this case, only one hardware circuit is sufficient. But by looking into previous problem, half waving effect problem, if you operate this circuit alpha not very close to pi, by giving sufficient time for thyristors to turn off, then what you can say, you can avoid that extra diode. Therefore, with one gate drive circuit, you can control very effectively this symmetric configuration. Now, the next topic is single phase full converter with discontinuous conduction. In the previous circuits, we assumed that load current was constant. Okay, that is possible with heavy inductance. But now, if load inductance is not sufficiently large, or due to this load EMF E, the rate of decay of current will be sometimes faster. Okay, so in such cases, what is the consequence? The load current may have discontinuity. What do you mean by discontinuity? We'll see now. Whenever you are discussing about discontinuous conduction, you should specify the load parameters. Now observe carefully. The notation in the circuit diagram is changed. I just consider load parameters because discontinuous conduction is possible with all types of loads. That means RLE load it is possible, RL load it is possible, R load is also possible. So discontinuous conduction, the main reason is load inductance may not be sufficiently large enough to maintain the conduction. Second reason is due to the presence of load EMF E, the rate of decay of current may be sometimes faster. These are the two things which will decide the continuity, whether it is a continuous or discontinuous. Now what we will do, first let us assume that the load is of RLE nature. Okay, load is of RLE nature. Now here just see the source voltage notation. VAB is blue color sinusoidal, VBA is the red sinusoidal, load EMF is E. So for the device to start conduction, we should give alpha greater than theta. So at omega t is equal to alpha, T1 T2 pair is triggered. That is the first point. Yet pi plus alpha, which is greater than this pi plus theta, pi plus alpha which is greater than pi plus theta. Second pair, that is T3 T4 pair is triggered. In the next cycle, that is at 2 pi plus alpha, T1 T2 pair is triggered. Okay, this is what the triggering sequence. Now what we will do, first let us consider that load is RLE type, RLE load. Okay, RLE load. Now with this load, suppose if T1 T2 devices are in conduction, if T1 T2 devices are in conduction, then what is the basic circuit equation? R into I naught plus L into d I naught by dt is equal to Vm sin omega t. R I naught plus L d I naught by dt plus E is equal to Vm sin omega t. So in our earlier half-wave rectifier circuit, we have solved this equation. Okay, we had some lengthy equation. From that, what was the conclusion? Output current will have two major terms. One is sinusoidal, another is exponentially decaying component. Okay, therefore first let us draw output current waveform. Now here T1 T2 pair is triggered at alpha, T3 T4 pair is triggered at pi plus alpha, right? So from alpha, see in our continuous conduction what we discussed, T1 T2 pair is triggered at alpha and that pair was in conduction until next pair started conduction because of heavy inductive property of the load. But now due to insufficient load inductance, what is the concept? T1 T2 pair will trigger at alpha. This pair is going to turn off before the next pair starts conduction. In that way, there will be discontinuity concept. Okay, so this particular I0 waveform will be from alpha to beta. Okay, alpha to beta here. So from alpha to beta, this is alpha and this is a beta, right? Now alpha to beta, what are the conducting devices? T1, T2 are in conduction. T1 and T2 are in conduction. Okay, so when T1 and T2 are in conduction, what is the output voltage? Now look into the circuit diagram. If T1 is on, X is connected to A. When T2 is on, Y is connected to B. Therefore, output voltage will be same as VAB. So what is VAB? Blue color sinusoidal. Okay. At omega t is equal to alpha, blue color sinusoidal magnitude is greater than the black color E. Therefore, we will have a little jump over here. Now, alpha to beta output voltage is VAB. Therefore, blue color sinusoidal waveform snapshot looks like this. Next, beta to pi plus alpha. Okay, this is pi plus alpha instant. Next pair is starting from pi plus alpha. Now beta, at beta first pair is turned off. Now my question is, from beta to pi plus alpha, what are the devices that are in conduction? Now see here, T1 T2 pair turns off at beta, T3 T4 pair starts after pi plus alpha. So beta to pi plus alpha, no devices will be in conduction. Therefore, there is no path for load current to flow. That is what a discontinuity means. Okay. So from beta to pi plus alpha, when there is no current flowing through the circuit, voltage across XY terminals, it is simply same as E. Therefore, from beta to pi plus alpha, I can draw output voltage is equal to load EMF E. Okay, output voltage is equal to load EMF E. Next, at pi plus alpha, look into the circuit diagram. T3 T4 pair is triggered. Therefore, what will happen? Load terminal X is connected to B, Y terminal is connected to A. Therefore, output voltage will be same as VBA. Again, the same RLE load is connected to sinusoidal source. Therefore, the same equation and same solution for I0 will be applicable. But that current waveform should start from pi plus alpha to, so here next cycle at 2 pi plus alpha, next cycle T1 T2 pair is triggered. But 2 pi plus alpha to, now let me draw output current waveform. Okay, pi plus alpha to this particular instant. So what is this angle? This angle is pi plus beta. Okay, this angle is a pi plus beta. Therefore, pi plus alpha to pi plus beta, what are the conducting devices? Conducting devices here are T3, T4 devices. Okay, conducting devices are T3, T4 devices. When T3, T4 are in conduction, then what is the output voltage? Output voltage will be same as that of VBA. Okay, let me take one reference line here and here also. So beta, pi plus alpha to pi plus beta, output voltage is same as that of VBA, that is a red color sinusoidal. Now at pi plus beta there is a discontinuity. At pi plus beta there is a discontinuity. Up to next pair is going to start conduction. Therefore, from pi plus beta to 2 pi plus alpha, okay, pi plus beta to 2 pi plus alpha, output voltage will be load EMF E during the discontinuous interval. Now after this, again the same waveform will repeat periodically. Again the same waveform will repeat periodically. This is how output voltage and output current waveforms. Now 2 pi to 2 pi plus alpha, this particular waveform portion will be same as that of 0 to alpha. Okay, 0 to alpha. So in this interval, output current will be same as that of 2 pi to 2 pi plus alpha. This is about V0 and I0 waveforms for RLE load. Okay, these are V0 and I0 waveforms for V0 and I0 waveforms for RLE load. Now by using this waveform analysis, let us calculate average output voltage. Okay, so what is that? Let us see. V0, average output voltage, V0 is equal to, what is the periodicity of that waveform? That is pi. So 1 by pi integration from alpha to beta. Now just go through the waveform. Alpha to beta, blue color sinusoidal. Equation for that blue color sinusoidal is Vm sin omega t d omega t plus integration from beta to pi plus alpha d omega t load EMF E and integration with respect to x-axis. Therefore, let us simplify this. 1 by pi Vm multiplied with minus cos omega t, limits are from alpha to beta, plus E into omega t, limits from beta to pi plus alpha. Okay, limits are from beta to pi plus alpha. Therefore, average output voltage we can write it as 1 by pi Vm multiplied with cos alpha minus cos beta plus E into pi plus alpha minus beta. Okay, this is the expression for average output voltage for RLE load. Now average output current can be written as V0 minus E divided by R. Okay, so this is V0 and I0 calculations for RLE load. Now the second possibility in case of discontinuous conduction is the load can be RL type. Now follow carefully. Here I will do a small modification. You need to redraw the waveform. Okay, of course you can also refer the lecture notes. Suppose if the load has only RL component, I just removed the EMF term E. In our half-wave rectifier analysis, what we discussed, for RL load and RLE load, output current waveform will have sinusoidal and exponentially decaying component. Therefore, for RL load also, there is no change in the current waveform. Okay, so current waveform remains the same as a sinusoidal and exponentially decaying component. But what is the difference? During discontinuity, that is during beta to pi plus alpha, follow carefully this interval. During beta to pi plus alpha, in the discontinuous interval, in the earlier case, load EMF was there. But now in RL load EMF is not there. Therefore, in this particular interval, output voltage is simply 0. Okay, output voltage will be simply connected to 0. And next cycle, V0 waveform will start from this point. In the similar manner, during discontinuity, here also output voltage will be 0. Output voltage will be 0. Okay, so this is what V0 waveform modification. Okay, this is a V0 waveform modification. In the similar manner, during discontinuous interval, output voltage will be 0. Here also I can remove it like this. Okay, just for your practice, you need to draw all of these waveforms, right? So don't feel that by just watching the video and looking at the lecture notes, you will remember all of these things. You should have thorough practice. Unless you understand the concept, you cannot draw the waveform. If waveform is not understood, how can you find the formulas? Okay, so my sincere suggestion, draw the waveforms. Okay, repeatedly I am telling. Now, this is modification in V0, and of course there is no modification in the I0 waveform. So this is the set of V0 and I0 waveforms for RL load. Now, in order to find average output voltage, what are the limits for V0 function? Here alpha to beta, the blue color sinusoidal. Therefore, for RL load, what is the expression for average output voltage? 1 by periodicity, 1 by pi, integration from alpha to beta, Vm sin omega t d omega t. Vm sin omega t d omega t. Therefore, Vm by pi integration for sin omega t is minus cos omega t, and limits are from alpha to beta. So V0 is equal to Vm by pi multiplied with cos alpha minus cos beta. V0 is equal to Vm by pi into cos alpha minus cos beta, and average output current is equal to V0 by R. This is about the RL load. The next possibility is the load is just a resistor. There is no energy storage element in the load side. Therefore, when T1 T2 pair is triggered, that is at alpha, output voltage will just follow VAB waveform, right? V0 will be simply follows V0 waveform, VAB waveform. In case of resistive load, what is our discussion? Output current will simply follows output voltage. Okay, so in this interval we can write conducting devices are T1 and T2. Okay, conducting devices are T1 and T2. Next, at pi plus alpha, T3 T4 pair is triggered. But what is the point here? At omega t is equal to pi, current flowing through T1 T2 pair has zero crossing. Therefore, now you just think about what are the conducting devices from pi to pi plus alpha. T1 T2 pair is turned off at pi. T3 T4 will start after pi plus alpha. So, in this interval, no devices will be in conduction. Hence, there will be discontinuity. Okay. T3 T4 pair is triggered at pi plus alpha. Hence, output voltage will be followed by VBA, that is from pi plus alpha to 2 pi. As the load is a resistive load, output current will simply has the same waveform shape as of output voltage. Okay, so in this waveform shape, output current T3 T4 pair will have zero crossing, yet omega t is equal to 2 pi. Yet omega t is equal to 2 pi. Therefore, 2 pi to 2 pi plus alpha, there will be discontinuity. Next cycle, T1 T2 pair will turn on at 2 pi plus alpha. So, from 2 pi plus alpha to 3 pi, output voltage will be followed by VAB. Okay, and I naught will be simply follows V naught waveform. So, these are the waveforms for resistive load. These are the waveforms for resistive load. Okay. Now, with this waveform, how can you find expression for average output voltage? That is, in case of resistive load, average output voltage V naught is equal to 1 by pi integration from alpha to pi Vm sin omega t d omega t. Vm sin omega t d omega t. Okay, so it will give you V naught is equal to Vm by pi into minus cos omega t. Vm by pi into minus cos omega t. Limits are from alpha to pi. So we will get V naught is equal to Vm by pi multiplied with 1 plus cos alpha. Okay, V naught is equal to Vm by pi multiplied with 1 plus cos alpha. This is the expression for average output voltage. After this, you can write I naught is equal to V naught by R. Okay, these are the equations for resistive load. Now, if you observe carefully here, single phase full converter for different types of loads, we are getting different V naught expressions. That is the reason I told earlier, 2 Vm by pi cos alpha is valid only for continuous conduction, not for discontinuous conduction. Now, let us see one more case in this discontinuous conduction. Now, the next possibility is load side R and E. Okay, load side R and E. Now, in this particular case, suppose if T1 T2 pair is turned on, let us look into the basic equation. RE load, in case of RE load, when T1 T2 are on, when T1 T2 are on. Okay, so here R into I naught plus E is equal to Vm sin omega t. Therefore, we can write down here I naught is equal to Vm sin omega t minus E divided by R. Okay, so we had a similar equation even in half rectifier also. So what was the conclusion then? I naught is also having the same waveform shape as of V naught waveform. But remember, I naught will be 0 whenever Vm sin omega t is equal to E. That will happen at omega t is equal to pi minus theta. Now let us see that. Now here, before alpha, no thyristor pair will start conduction, and hence output voltage will be equal to load EMF E. Next, T1 T2 pair started conduction at alpha, and it will conduct up to, now observe carefully here, I am extending pi minus theta line now. Till now I didn't extend this line. Okay. So this particular line is pi minus theta. So alpha to pi minus theta, T1 T2 pair is in conduction. In that interval, output voltage will be same as that of source voltage, that is VAB. I naught waveform will simply follows V naught waveform in such a way that I naught will reach us to 0 at omega t is equal to pi minus theta. So in this interval, what are the conducting devices? Those are T1, T2 or the conducting devices. Next, from pi minus theta to pi plus alpha, there is a discontinuity. During that discontinuity, output voltage will be load EMF E. Next, at pi plus alpha, okay, to this particular instant. What is this instant? That is 2 pi minus theta. So pi plus alpha to 2 pi minus theta, conducting devices are T3 T4 devices, right? So when T3 T4 pair is in conduction, output voltage will be same as that of VBA. Output voltage will be same as that of VBA, and I naught will simply follows V naught. So I naught will reach us to 0 at 2 pi minus theta. So in this interval, what are the conducting devices? T3 T4 are the conducting devices. Okay. Now 2 pi minus theta to 2 pi plus alpha, there is a discontinuity. So in this discontinuity, output voltage is equal to load EMF E. Now 2 pi plus alpha to 3 pi minus theta, this is 2 pi plus alpha and this is 3 pi minus theta. In this interval, output voltage will be same as VAB, blue color sinusoidal, and output current will be same as that of output voltage. Okay, this is how V naught and I naught waveforms will be for RE load. Okay, this is for RE load, right? Now for this particular waveform, let us find average output current first. RE load in the half wave rectifier circuit, I told already, average output current 1 by periodicity, that is pi, 1 by pi, integration from alpha to pi minus theta. What is the current function? Vm sin omega t minus E divided by R d omega t. So let us simplify this equation. 1 by pi R Vm into integration for sin omega t minus cos omega t minus E into omega t minus E into omega t. What are the limits? Alpha to pi minus theta. Therefore, it will give you 1 by pi r Vm. Now substitute the limits. Upper limit will be cos theta, lower limit is minus of minus plus cos alpha minus E into pi minus theta minus alpha. Okay, this is the expression for average output current. Once we got average output current, how can you write expression for average output voltage? V naught is equal to R multiplied with I naught plus E. Next, let us look into single phase semi converter with discontinuous conduction. Now in this particular circuit, in the previous topic, continuous conduction, we considered that there are three configurations, right? First one is symmetric configuration. In that, upper half devices were thyristors, lower half devices were diodes. Second one was asymmetric configuration. Both the configurations were formed by one thyristor and one diode. Third topology was full converter with a freewheeling diode. Now, if you refer back your waveforms, you can notice that in all the three configurations, pi to pi plus alpha, so here pi to pi plus alpha, there was a freewheeling action. In the similar way, 2 pi to 2 pi plus alpha also there was a freewheeling action. But in case of discontinuous interval, what is that modification? Whatever freewheeling action was from pi to pi plus alpha in our earlier circuit, now that freewheeling action will finish before pi plus alpha itself. Okay, before pi plus alpha itself. That is at the instant beta. So beta to pi plus alpha there was discontinuous conduction. In the similar way, 2 pi to 2 pi plus alpha, నువ్వు నవ్వకరా కొడతా నవ్విదే ఫింగరే అరే కుష్వాంత్ ఫింగరే 2 pi to 2 pi plus alpha, earlier freewheeling action, now it will finish at pi plus beta. Okay, so before going to the waveforms, first let us write down one table. What is that? Alpha to pi conducting devices are first and second position devices. Next, pi to beta, there was freewheeling action. Next, beta to pi plus alpha, it was discontinuous conduction. Next, pi plus alpha to 2 pi, third and fourth position devices are in conduction. 2 pi to 2 pi to pi plus beta, it was freewheeling action. Next, pi plus beta to 2 pi plus alpha, this is discontinuous conduction. Okay, now in case of first configuration, what are the devices at first and second position? That is T1 and D2. Whereas in the second configuration also the devices are T1 and D2. In the third configuration, these devices are T1 and D2. Now coming to freewheeling action, in the first configuration, that freewheeling action can be provided by T1 and D4. In the second configuration, that freewheeling action was provided by D3 and D2. In the third circuit, that freewheeling action can be provided by FD. Okay. Next, during discontinuous interval, no device can be in conduction. Therefore, simply put cross mark. Next, third and fourth position devices in the first configuration T3 and D4. In the second configuration D3 and T4. Third configuration T3 and T4. Now the freewheeling action here T3 D2, here D3 D2 and here FD, and during discontinuous interval no device will be in conduction, hence you can simply put a cross mark. Okay, now by using this, let us draw V0 and I0 waveforms first by taking load components are RLE load. Load components are RLE load. So what is the basic idea for RLE load? I0 waveform will be having sinusoidal and exponentially decaying component from alpha to beta. Okay, alpha to beta, it is having sinusoidal and exponentially decaying component. Now at omega t is equal to beta, there is a discontinuity. From beta to pi plus alpha, there is a discontinuity, right? So now in this interval, again, what is the subdivision? Alpha to pi conducting devices are at first and second position. What are the devices names? You can get it through table. Okay, pi to beta, there is a freewheeling action. Pi to beta, there is a freewheeling action. Beta to pi plus alpha, it is discontinuous conduction. Okay, now let us draw output voltage from alpha to pi. Okay, alpha to pi, V0 waveform is blue color sinusoidal. Okay, alpha to pi, output voltage is blue color sinusoidal. Now pi to beta freewheeling action. During freewheeling action output voltage is 0. Okay, next beta to pi plus alpha. Beta to pi plus alpha, what is output voltage? During discontinuous interval output voltage is load EMF E. Next pi plus alpha to pi plus alpha to pi plus beta. Okay, pi plus alpha to this instant is this is pi plus alpha, this instant is pi plus beta. Okay, pi plus beta. Now in that pi plus alpha to 2 pi, third and fourth position devices are in conduction. 2 pi to pi plus beta, it is freewheeling action. Pi plus beta to 2 pi plus alpha, it is discontinuous conduction. Therefore, pi plus alpha to 2 pi, pi plus alpha to 2 pi, output voltage will be same as that of VBA. Okay, red color sinusoidal. Now 2 pi to pi plus beta, it is freewheeling action. 2 pi to pi plus beta, it is a freewheeling action. Pi plus beta to 2 pi plus alpha, there is discontinuous interval. During that discontinuous interval, output voltage is equal to load EMF E. In this way, the waveform will repeat periodically in the next cycle again. This is how V0 and I0 waveforms. 2 pi to 2 pi plus alpha, this waveform will be same as that of 0 to alpha. Okay, so 0 to alpha, the interval will be same as that of 2 pi to 2 pi plus alpha. So these are the waveforms for V0 and I0 for particularly to RLE load. Now, by using this waveform, let us calculate average output voltage. Okay, so RLE load, what is average output voltage? V naught is equal to, periodicity is pi, therefore 1 by pi integration from alpha to pi, and blue color sinusoidal Vm sin omega t d omega t plus integration from beta to pi plus alpha, output voltage is equal to E d omega t. Okay, therefore what will be the conclusion from this? 1 by pi Vm, this simplification you will get 1 plus cos alpha plus E into pi plus alpha minus beta. I hope you can understand this system. This is the expression for average output voltage in case of RLE load. So, what is the expression for average output current? That is V naught minus E divided by R. Okay, this is the expression for RLE load. Now here, let us take small modification. For example, if the load is not having EMF term, follow carefully here, I just removed EMF term. So in our previous discussion again, we discussed that in case of RL and RLE load, output current waveform shape remains same. Therefore, what is the only difference? That is during discontinuity, this beta to pi plus beta to pi plus alpha, during discontinuity output voltage is simply 0. It is not having any EMF term. In the similar manner, beta to pi plus alpha, output voltage is 0. There is no EMF in the load side. Therefore, here also during discontinuous interval output voltage is 0. Okay. So one of the important conclusion is in our previous analysis in the semi-converter continuous conduction, we got pi to pi plus alpha output voltage was 0. That was due to completely freewheeling action. But now freewheeling action is up to beta only. But beta to pi plus alpha, the reason for output voltage is to be 0, that is discontinuous interval. So we can have one conclusion here. In the rectifier circuits, output voltage is 0 in two situations. One is during freewheeling action and the second one is during discontinuous interval if the load has no EMF. Okay, so we can have that conclusion. Now from this waveform, let us look into the expression for average output voltage for RL load. Okay, average output voltage expression for RL load. So what is capital V naught equation? 1 by pi integration limits or 1 by pi periodicity, 1 by pi. Limits are from alpha to pi Vm sin omega t d omega t. Vm sin omega t d omega t. Therefore, it will give you Vm by pi minus cos omega t, limits from alpha to pi. So from this we can get V naught is equal to Vm by pi multiplied with 1 plus cos alpha. Okay, 1 plus cos alpha. After this, how can you express I naught? That is equal to V naught by R. I naught is equal to V naught by R. Let us take a resistive load. Okay. So in case of resistive load, at omega t is equal to alpha, due to first and second position devices conduction, output voltage will be followed by VAB. So we know that for resistive load, output current will simply follows output voltage. Therefore, I naught waveform will be same as that of V naught waveform. So at omega t is equal to pi, the current reaches to 0. Okay. So here from alpha to pi, first and second position devices are in conduction. Next. So here one of the important point to observe, in case of resistive load, there is no point of freewheeling action. Therefore, pi to pi plus alpha, this interval considered as discontinuous interval. Okay. Next, pi plus alpha to 2 pi, third and fourth position devices are in conduction, and hence output voltage will be equal to VBA. Okay. So as the load is resistor, output current will simply follows output voltage. Therefore, pi plus alpha to 2 pi, third and fourth position devices are in conduction. Next, 2 pi to 2 pi plus alpha, this is discontinuous interval, and 2 pi plus alpha onwards, again the same waveform will repeat periodically. This is about V naught and I naught waveforms for resistive load. If you observe carefully, V naught expression, you will get the same as that of RL load from the previous discussion. Therefore, we need not to go with the equations. Here I can write simply the same equations are applicable for resistive load also. Next, let us look into another case, that is RE load. That is for RE load. In the previous topic, single phase full converter also, we discussed about RE load. Now again RE load with a single phase semi converter. Strictly speaking, for RE load, full converter and semi converter will give the same outputs. So what is that? Before alpha, no devices pair will be in conduction. Hence, output voltage is equal to load EMF E. Yet omega t is equal to alpha, first and second position devices will be in conduction. So alpha to this interval. So this instant is pi minus theta. Alpha to pi minus theta, output voltage will be followed by VAB, and output current will simply follows output voltage. Okay. So here first and second position devices are in conduction from alpha to pi minus theta. Now from pi minus theta to pi plus alpha, there will be discontinuity. So in this discontinuous interval, no devices will be in conduction, hence output voltage is equal to load EMF E. Next, from pi plus alpha to 2 pi minus theta, third and fourth position devices will be in conduction, hence output voltage is equal to VBA. Therefore, output current will simply follows VBA, right? So in this following, this I naught will be 0 at 2 pi minus theta. Okay. So in this interval, third and fourth position devices are in conduction. Now from 2 pi minus theta to 2 pi plus alpha, there is discontinuous interval. Okay. Now at 2 pi plus alpha, then what happens? Again, the VAB, same waveform will repeat periodically. Okay. This is how V0 and I0 waveforms. So at this instant, output voltage will be load EMF E. These are the waveforms for single phase semi converter RE load. Okay. So with this I0 waveform, if we look into average current expression, average output current expression, what we will get? I0 is equal to 1 by periodicity, 1 by periodicity. Integration limits are from alpha to pi minus theta, and it is Vm sin omega t minus E divided by R d omega t. Vm sin omega t minus E divided by R d omega t. Therefore, what is the simplification? 1 by pi R Vm, in fact, we already derived this equation in the single phase full converter, previous topic. So we will get cos theta plus cos alpha minus E into pi minus theta minus alpha. Okay. So this is the expression for average output current. This is the expression for average output current. Now, from this, average output voltage can be written as R into I0 plus E. Now, if you observe carefully here, in all this explanation, there is one sequence. We started full wave rectifier with the continuous conduction first. Center type configuration, full bridge, after then half bridge, semi converter. Next we discussed discontinuous conduction with the RLE load, RL load, R and RE load for single phase full converter and semi converter. So with this I covered all the varieties. Okay. Now we'll take up more numerical examples in the next lecture. Thank you.